Hi everyone, so let's go ahead and continue with 2.5. Last time when we were talking about horizontal asymptotes, we mentioned that if the numerator has a higher degree and the denominator has a lower degree, there is no horizontal asymptote. But then I said as a note, if the numerator has a higher degree by 1, then there is what we call an oblique asymptote. And that's what we're going to focus on today. All right, so an oblique asymptote happens when the numerator has a higher degree, but only by 1. Okay, so how do we find the oblique asymptote? Well, basically, we have to do polynomial long division. All right, but before we get into that, let's run through our routine here. So let's figure out what the domain is, right? The domain here is everything except -3, so negative infinity to -3, -3 to infinity. The vertical asymptote is x equals -3. Okay. All right, so horizontal asymptotes, this one doesn't have any, so we just say none. But if you look at the degree here and the degree here, you see that x squared, right? The exponent is 2 on top, but only 1 here on the bottom. So we need to find the oblique asymptote. Now, in previously, this used to be called a slant asymptote, right? But they're the same thing. Okay, so the way in which you have to do this is you have to do polynomial division here, right? So depending on what type of functions you have on top and on the bottom, you either have to do long division or you can get away with synthetic division, right? So in this case, we can totally get away with synthetic division. So let's go ahead and do that. We're going to put -3 out here. And then what do we put here? 1, 1, -8. 1 comes down, -3, -2, +6, and the remainder is -2. All right, so for the purposes of this, we're just going to throw away the -2. Just throw away the remainder. We don't need it. What we're going to focus on is this. This polynomial here is y equal to, we started with x squared, so this is just x minus 2, and this is your oblique asymptote. Okay, now if you need to find the zeros here, you would just say x squared plus x minus 8 is equal to 0. If it's something that can be factored, you can factor it and get the zeros. In this case, you can't factor this one, so you would have to do the quadratic formula for this. But let's hold off on that for the time being. Okay, all right, so we have a vertical asymptote here at -3. And the oblique asymptote is y equals x minus 2. And we graph that, right, just like we did in the old days. So this is like, you know, a little bit of like throwback Thursday here, right? So mx plus b, the y-intercept is -2, and I go up 1/1. So I graph this line. Okay, this is that oblique asymptote. This is y equals x minus 2. It is still an asymptote. Okay, next we need to graph this function. Okay, so if we had done the quadratic formula here, we would have gotten that the zeros here are -3.37 and 2.37. Okay, using the quadratic formula. So that's -3.37 is here, and then 2.37 is just here. Okay, so the way in which this looks, right, is it's going to have to follow the vertical asymptote here. All right, so only for the ones with an oblique asymptote will I let you use your graphing calculator just to graph. Everything else that we did here, 1 through 5, you should be able to do by hand, But then just to graph, because it's a little bit harder to visualize, I'll let you use your graphing calculator. So here it is. I've graphed it on mine right here, right? So do you see how it follows the the vertical asymptote on top there? So it'll come down like this. It'll come down like this, cross that x-axis at the 0, move further down, and then follow that oblique asymptote. Okay, and now look, it's the same sort of situation. You see how here it went off the screen to the left of the horizontal, to the left of the vertical asymptote. It's the same thing. It comes back up here from the bottom to the right of the vertical asymptote. And then again, it's got to go and follow these oblique asymptotes and move up like that. Okay, so as long as you show me all of the work here, you can use your graphing calculator to graph that part. Okay, so lastly, we need to add one other part to this, is what if you have a vertical, not a vertical asymptote, but a removable discontinuity. Okay, what does the graph look like then? So when the numerator and the denominator do have common terms which can be eliminated or canceled, this is when we get removable discontinuities, which we can also call holes, and they appear in the graph. So right at that point, you will have like this minuscule little pinhole almost where the graph is undefined. All right, so let's take a look at this example here. Just like we did last time, the first thing you do when you have something like this is you want to factor everything. Okay, so let's talk about domain. Okay, the denominator is 0 at +3 and -2. So the domain is -infinity to -2, -2 to 3, 3 to infinity. All right, that's the domain regardless of you have an infinite discontinuity, removable discontinuity, whatever type of discontinuity. That's the domain. Now, after this, let's take a look at which of these discontinuities is going to give us a vertical asymptote or a removable discontinuity. Because this cancels out and it ends up leaving us with x plus 3 over x plus 2, right? The term that gives us the vertical asymptote is this one, right? Same situation. That x plus 2 is not going anywhere. It is infinitely there. It is an infinite discontinuity. In other words, it is a vertical asymptote at x equals -2. Okay? Now, this other one, the x equals 3, went away, right? So there is a removable discontinuity or a hole at x equals 3. Okay. What about a horizontal asymptote? For that one, for the horizontal asymptote, I like to look back at the original function. It's easier. Because sometimes when we factor, some coefficients will get lost and so on and so forth. So when we go here, it's x squared over x squared. So the horizontal asymptote is y equals 1. Okay, what about the zeros? For the zeros, it's because the x minus 3's cancel, it's enough to just take the remaining x plus 3, set it equal to 0. So x equals -3. All right, so let's put some of this information on our graph here. So at x equals -2, there is a vertical asymptote. At x equals -3, there is a 0. Y equals 1 is a horizontal asymptote. And at x equals 3, there is a removable discontinuity or a hole, right? So that's at x equals 3. Now we need to figure out where is it? Is it here? Is it here? Is it here? Is it here? Right? Where is it? And this is where we get in a little bit of like a notation sort of controversy, right? Technically, at x equals 3, this function is undefined. So you are in no way able to write down at x equals 3, y equals this number. However, we are going to cheat just a little bit, right? We're going to cheat just a little bit. So let's take a look at the location of the removable discontinuity. Okay, and what I want to do is very, very briefly, now don't get caught doing this, but very, very briefly, I'm going to take the remaining function here, and very, very briefly, I'm going to put in x equals -3 over there. Okay, so when I do that, I'm sorry, not x equals -3, x equals +3, right? Very, very briefly, I'm going to put in x equals +3. So what do I get? 3 plus 3 is 6 over 3 plus 2 is 5. So 6 over 5. So the location of that is at 6 over 5, which is like 1 point something, right? So at x equals 3 and 1 point something, right there is where my removable discontinuity is. Now, you can never say at x equals 3, y is 6 over 5. You can never say that. You can never be caught with that, right? You can think it maybe for a split second, but you can never say it because technically the graph is undefined at that point, right? But that's a very efficient way to find where to put that hole. So now, since the graph crosses the x-axis at x equals -3, this is going to look like this. And then it comes back from the opposite side. And there's a hole there, so it just touches it there and then moves on. Okay? All right, so that's how we graph that one. And make sure this little hole is visible there. Okay. All right, last but not least, let's talk about solving rational functions. You've done this back in algebra too. Okay? To solve a rational function or a rational equation, you want to multiply each term by the LCD of all the terms of the equation, okay? And then after that, you want to make sure to check for extraneous solutions. Okay, so it says here to solve the following functions, state any restrictions. Restrictions are basically discontinuities. So for the restriction, take a look at here. The denominator has x minus 6 in there, right? So we know from there that x cannot equal 6. That is the restriction. Okay, so what we're going to do here I have x over 1 and then 4 over x minus 6. The common denominator between 1 and x minus 6, the LCD, is x minus 6. So I multiply every single term by x minus 6. You got to be inclusive here, right? No discriminating. All right, so what we get first is x times x minus 6 minus 4, because the x minus 6's cancel, equal to 0. X squared minus 6x minus 4 is equal to 0. Here, if you can factor, you factor. Unfortunately, this one you can't factor, so we got to do the quadratic formula. Negative b plus or minus the square root of b squared minus 4 times a times c all over 2. So this is 6 plus or minus 52 over 2. 6 plus or minus 2 root 13 over 2. So x is 3 plus or minus root 13. Okay? None of these are the restriction, so we're good. Okay? So those are the solutions. All right, let's take a look at another one. What I want to do here first is factor. And when I factor, I get x minus 6, x plus 3. Okay, so I have an x plus 3, x minus 6, and so on. Let's write the restrictions. And here, x cannot equal -3, and x cannot equal +6. Okay. I want to multiply by the LCD, which is x minus 6, x plus 3. Multiply every single term by that. Okay, let's see what cancels. The x plus 3's cancel here. X minus 6's cancel here, and everything cancels here. The most important thing here is bookkeeping. You just want to make sure that you don't lose sight of any terms because that's very, very easy to do. Okay, so what I have here is 2x times x minus 6 plus 3x plus 3 equal to 27. So I have 2x squared minus 12x plus 3x plus 9 equal to 27. Bringing everything to the same side, I get that 2x squared minus 9x minus 18 equals 0. Let's factor. I get plus 3 minus 6. Okay, so here I get x is equal to negative 3 over 2, and x is equal to 6. But since 6 is a restriction, I cross it out, so the only solution is negative 3 over 2. Okay? Okay, and finally, take a look at this. This over here is called a lens equation, right? And so basically when you have a lens and you have the object here, you can see the image, behind the lens. So but all you need to know here is F is the focal length. This is F. DI is the distance from the lens to the image, this one. DO is the distance from the lens to the object. And it says here, suppose the image is 10 centimeters from the lens. So basically DI is 10 centimeters. And the focal length is 6. So F is equal to 6 centimeters. Write a rational equation to model this situation. Okay, we can do that. The equation is, and of course, whenever you're given problems like this, you're always going to be given the equation, right? Nobody expects you to know this stuff. 1 over F is equal to 1 over DI plus 1 over DO. So believe it or not, this is the only formula that, your optometrist uses to calculate what kind of lens you need, right? Except the machines do it for them. Okay, so F is 6, 1 over 6 is equal to 1 over DI, which is 10, plus 1 over DO. So that's it. That's the rational equation that models this situation. Okay? Easy as pie. Next, find the distance from the lens to the object. So we need to find DO. Okay, fine. We just multiply. We just solve this equation. Okay? All right. So between the 6 and the 10 and the DO, what is the LCD? Well, it's 30 DO, right? So 30 DO, 30 DO, 30 DO. Okay, the D's cancel here. And so let's see what we get. 30 DO divided by 6, that gives me 5 DO is equal to 3 DO plus 30. Subtracting, I get 2 DO is equal to 30. So DO is equal to 15. So my answer is 15 centimeters, right? And that's that. That's the end of section 5. You can now go ahead and